Today we continue with our class and principles of programming languages, and we actually are going to talk about logic programming. So this is a class on principles of programming languages. It basically covers a lot of topics, including multiple different paradigms of programming languages. So today we'll discuss about Prolog, programming in logic, a logic programming language that is in fact one of the most famous logic programming languages. Stony Brook in fact develops two such logic programming languages, AccessBeProlog, which follows the standard ISO Prolog. It's an international standard for Prolog systems, and it also implements an object-oriented logic programming language called Flora. These are like database programming languages. Basically, they are programming languages and they mirror the procedural execution in some respects of imperative programming languages. However, they map directly to first-order logic, and internally they actually compute the logical consequences of a set of logical formulas. But we will go into details in a couple of seconds. Now, in preparation for this class, I compiled AccessB for all the platforms available, and you can download the zip file, or you can actually compile AccessB from scratch yourself. It's described in the manual, and I'm using Stony Brook Prolog for patriotic reasons, because we are at Stony Brook, but you can use any Prolog system you like. In fact, what I mentioned on Piazza is that we use standard Prolog in this class, so you can use any Prolog system, including online versions like Swish. And here is an example of Swish, where the program is written on the left-hand side and is compiled, and we run queries against that program. I personally prefer to actually write programs on in editors like Notepad++ and then compile them on my own machine with AccessB. So I described what to do with the AccessB compilations that I created. For instance, you can add your path to accessb.exe for your correct platform. In my case, that was in config x64, the 64-bit version for PC Windows. If you want to find out how to add paths to your path environments, just Google it. It's very easy. For instance, if you copy this and you drop it in your preferred search engine, it will basically tell you. For Windows, for instance, once you open your File Explorer, you can go to Properties and Advanced System Settings, Environment Variables, and in Environment Variables you can select Path, and you can add as a new path. In my case, I added the AccessB Prolog version, the bin version from config. I recommend that you do exactly the same thing, but it is up to you. Okay, good. So today we'll cover AccessBeProlog, and we'll write programs in AccessBeProlog, and we'll continue with this next class before the final exam. So at the beginning of the semester we talked about paradigms of programming languages, and we said that there are imperative programming languages that basically make changes to memory, and then they basically you execute like a Turing machine. You read the input on the tape and you basically do an output, either write on the tape or advance to the next state or skip several states and so on. So that is imperative programming. Basically, it's like procedural programming. You execute statements in order and they do changes to memory. We learned several different versions of imperative programming, procedural programming, when you learned C or basic Java programming with loops, with if statements or selection statements, with assignments because they modify memory and so on. Then we learned SML. SML is a functional programming language. It basically, we define functions. It matches actually the syntax of functions in mathematics. There is also a mathematical formula is called lambda calculus that actually is this definition of functions, including if functions do not have names. And today we actually talk about a third paradigm called logical programming or logic programming. This matches first order logic or first order predicate calculus, and AccessB and its variants make the most commonly used logic programming paradigms. One variant, as I mentioned, is the AccessBeProlog, developed here at Stony Brook University. Other Prolog systems include SWI, Sixtus, YAP, Chao, GNU Prolog, and they all follow, or most of them follow, what is called the ISO standard. It's a standard basically submitted to the International Standards Organization, and it basically defines what the language standard must follow. Now, there are many other logic programming systems that are developed following either paradigms, not only first order logic. They follow logics closer to the intuition of human intuition. For instance, even logic Prolog itself includes something called negation as failure, and also cuts, which are basically, it cuts the search tree of solutions. And these are kind of imperative features. We'll talk more in detail a little bit later, but all of these different paradigms, either that you do answer set programming, and there are many systems in that area like DLV and Klingo or Potasco with Gringo, and a few tools that are available in logic programming, and they make basically a lot of progress. Including this summer there is a conference at Oxford, in the International Conference on Logic Programming. So what exactly logic programming does? It basically deals with relations. Relations are building blocks on predicate calculus. For instance, relations are named like P of a set of arguments A1 to AK. For instance, parent of XY. It may mean that X is the parent of Y, or it may also mean, if we give that intuition, that Y is the parent of X, or X has the parent Y. But basically, we attach meanings to these relations, but within the logical system, they are simply structured building blocks with no meaning beyond the provided explicitly state relationship, basically that X is the first argument and Y is the second argument of parent. Now, you can actually also think about this as a tuple in a relational database, that we have the parent table and one tuple as the first argument X, and the second one as the second argument Y. And here is an example. Let's consider that we have a case that I later actually show it as a graph, that Pam is the parent of Bob, Tom is the parent of Bob, Tom is also the parent of Liz, Bob is the parent of Anne, Bob is the parent of Pat, and Pat is the parent of Jill. So we can basically represent that as a set of relations. In Prolog we call them facts. Every fact terminates with a period, and they are basically axioms. We know them to be true. The external world or someone told us that these are all true, that Pam is the parent of Bob, and so on. So one thing that you can see is that these relations have an arity. Arity is the number of arguments that every relation has. So for instance, parent has an arity of 2. Always the parent predicate comes with 2 arguments. Male has an arity of 1, and it basically states that the argument X is a male. So in this case, Tom is a male, Bob is a male, Jim is a male, and so on. So Prolog basically takes these as inputs. They are called axioms, and in fact we can query them directly. We can query like who is the parent of whom, or who are the parents of Bob, or who are the parents of Jim, or who are the children of Tom, and so on. So if you, and now this is the practical part of the class, if you actually want to try these examples that you find in the lecture notes, you can create a text file, and let's create a text file on the desktop. So I'm going to call it family.pl. PL is the extension of Prolog in general. There are also systems that accept P as an extension, uppercase P. I will use PL, and let's open this file and actually paste the facts that we had previously defined in the presentation, in the slides. So for instance, these are all facts stating facts that are known in the database, that Pam is the parent of Bob and so on. So I saved the file. You can add additional facts. For instance, we can add the 3 males that are known in the system, and later we'll add other facts like who are the females and so on. Or we can write rules, basically stating that those persons that are not male are female. Okay, but we'll talk about that a little bit later. So once we save the file in Prolog, in general, we actually start AccessBeProlog. So in this case, I put the file on the desktop, so I change to the desktop. I start AccessBeProlog, and I compile the file family. And there are many different ways to compile a file. If it takes the extension PL, you can just put the name of the file within brackets, and then it will actually find the file and compile it. And it basically tells us that now we compile the file family. So the same way that we did above, if you have a different extension, you can actually specify it within an atom. So family.pl in our case, again within square brackets, and it compiled that file. There are many other commands, like for instance consult for the same file family.pl, also loads the file and basically compiles it. Okay, so now we can ask queries. So in this case, this file contained facts about families. I will show you again the original file, and now we can ask who are the parents of Bob. And we can see that the parents of Bob are Pam and Tom. The system gives us one answer at a time, and if we want more answers, we type semicolon and it gives us more answers. Now the good part about Prolog, because it's a proof, it's a theorem prover, you can actually ask questions with either arguments bound or free. So in this case, I'm asking who are the children of Bob, and it will tell me that Anne and Pat are the children of Bob. If I want to ask who are all the parents of all the children, it will give me tuples. Pam is a parent of Bob, Bob is a parent of Anne, and so on. Now let's assume that I want to write a query that makes a join between the two tables. So who are the parents that are males? Basically we are asking who are the fathers in this program. So we are asking who are the parents X to Y, such that X is a male. And the system tells us that Bob is a father to Anne, and similarly, if we want more answers, we can ask with semicolon, and it will enumerate all the parents that are males. So in this case, Bob is a male and the parent to Anne. Tom is a male and the parent to Bob. Bob is a male and the parent to Pat, and Tom is a male and the parent to Liz. You can even join the same tables. So for instance, I would like to ask who are grandparents. Basically, those parents whose children have other children themselves. So I can ask it as, give me parent X to Y, such that Y is a parent to Z. And now it will give me that Pam is a parent to Bob and Bob is a parent to Anne. So in fact, Pam is a grandparent to Anne. And we continue basically getting all the grandparents. Now if I want, for instance, give me all the grandparents that are male, so grandfathers, I can actually ask it as male X and parent and so on. So that will give me exactly the same answers as, it will give me answers that are grandfathers, basically. Now, one thing about Prolog is that it's logic. So in a conjunction, it doesn't actually matter the order. So, for instance, it is male x, parent xy, parent yz is the same with parent x to y, male x, and parent y to z. So the order of arguments should not matter. Now this is true in general about Prolog. The order of, not arguments, the order of goals does not matter. But we will see that in fact in Prolog, it always, for every query, it always starts from the top of the database to find answers for that query. And in a query like this one, it always starts from left to right. So it actually solves first parent, then it solves x, then it solves parent, and so on. So there is an implicit order in the execution of Prolog programming language. And that order is that conjunction is executed from left to right. And when we actually execute a query over the database, we basically start from the top of the database to the bottom. So the first answer that it will give us for instance, parent x to y is in fact the first one in the database. And this continues to the next ones and so on. So it's Pam to Bob, Bob to Ann, Tom to Bob, and that's exactly what we got here. Okay? But let's continue with the lecture, and then we'll see more examples as we basically go through the lecture. So again, predicates are building blocks. They always have this form that we give a name, there's the predicate name, and the arguments of that predicate. So another example is that we have females defined in the program, and Pam, Pat, Ann, and Liz are females. These are axioms. They are basically called facts in Prolog. So if we have that big example that we saw up to now, we represent it as a set of facts. Okay, but the power of Prolog doesn't come only from facts. It also comes from logic and rules. So let's actually define in logic, how do we define a mother? So in first of the logic or predicate calculus, we would write a logical formula like the one that we have below. For every x and y, if x is a parent to y and x is a female, it implies that x is a mother to y. Now in Prolog, this will be written in reverse order. Basically, x is a mother to y if x is a parent to y and x is a female. So two things that you observe from translating from first of the logic into Prolog. It would be that the quantifiers are implicit. So in Prolog, we do not quantify variables. All the variables are universally quantified over the entire rule. And that we don't use the arrow for implication that we used in CSE307 for basically writing logical formulas. This is a universal implication. We actually use the colon dash, and is actually read as if. So the conclusion is to the left of the premise of this rule. So what we are basically translating this rule in natural language would be that x is a mother to y if x is a parent to y, and so we read the comma between sub-goals as a conjunction, and x is a female. So all the variables are universally quantified outside the rule. We will see what that means. It basically means that all the variables are universally quantified outside the rule, but if there are variables that only occur in the body of the rule because of the logical equivalence, that in fact implication is equivalent with this or the negation of this, then we have a negation of the conjunction and the universally quantified variables becoming substantially quantified in the body of the rule. We will see what that means in a couple of minutes. I will show you how to read Prolog rules in different cases, where variables occur in the head, when variables occur in the body. But before we continue, I want to make sure that this logical formula is understood by everyone. basically the universally quantified formula above in first of the logic is understood. So again, we cover in this case material from the foundations of computer science, which is covered in the course CSE307 at Stony Brook, and in predicate logic we basically have universally quantified formulas. In this case we are saying that for all x and y's we want this to be the mother of x, y to be implied by all the possible bindings of x and y for which the premise is true. So the universally quantified variables outside the rule basically are stating the fact that we infer all the possible mothers x to a child y. Okay? So I hope that the formula in first of the logic is understood. Otherwise, everything else that we will continue doing as rules is going to be a little bit difficult. So any questions up to now? Okay. So more relations, or more rules in fact. For instance, we want to state that x is a grandparent to y if x is a parent to z and z is a parent of y. So actually write it in Prolog as a rule that states that we infer a new relation, grandparent, between some x and some y. In this case, I'm actually showing it for a specific query, and this grandfather x to y is true if x is a parent of some z, if there exists a z such that x is a parent of that z, and z is a parent of y. So for instance, this would respond to a query, who are the grandparents of Jim? Because basically if we bind y to Jim, then we are looking for those parents of Jim who are children of the grandparent x. Now we can also ask many other questions. We can actually ask questions, who are grandparents to what children, or who are actually the grandchildren of some known person. Like we can actually bind y x to some value. Now how do we actually write siblings? Like for instance, what are the siblings of n? We can basically define the rule sibling. X is a sibling of y if z is a sibling of x, and z is a parent of x, and z is also a parent of y. However, we don't want to obtain that people are siblings to themselves, because the first conjunction will also succeed for values where x and y are the same, because we basically get that that z is the parent of x, z is the parent of y, x and y could be the same, but we actually state that I want as siblings only those that are different than y. So I will basically get that x and y are siblings if they are different, and z is the parent of x and z is the parent of y. Like for instance, I can get who are the siblings of n by actually finding who are the parents of n and what are other children of those parents z, such that n and y are different. Okay. And many other relations can be written. Grandparent, great-grandparent, cousin, great-great-grandparent, and so on. In fact, I would like to do an experiment. So, in fact, let's actually try to write all of these family possible relationships for all of the facts that we have in the database. So, first we are going to add the female facts. So, all of those people that we have in the database that are not stated to be males, I will state them to be female. Okay. So in this case, I'm going to add Pam, Anne, Liz, Pat, and that's it. I believe I didn't miss anyone. So now we add rules. So we had the mother relationship, the first rule that we wrote, and we said that x is a mother to y if I personally prefer in the style in which you have one fact per line. So this way is easier to read and easier to see if you are actually missing any kind of commas for conjunction or periods and so on. So I will write it in this style. Please follow it. It's actually, there is a paper by Michael Covington and Jan, the creator of AccessBeProlog, that actually describes this as the most preferred way to write Prolog programs. Prolog ignores white spaces like in Java, and in C. So in fact you can write the entire rule in one single line, and you can write multiple facts per line, but it will be very difficult to read such a program. So we said that X is a mother to Y if X is a parent of Y and X is a female. We can also write a rule for father. So X is a father of Y if X is a parent to Y and X is a male. And the order of the conjunctions does not matter. So in fact I could have written if X is a male and X is a parent to Y. So this does not change the answers. I mean, it changes the order of answers, but otherwise it doesn't really change the answers. Okay, so now we also had a sibling. So X is a sibling to Y if they have a common parent Z to X, and parent Z to Y, and X is different than Y. So this is like not equal. Basically we want to represent not equal, and instead of cutting the equal, we actually use this slash, backward slash equal for stating that X and Y do not match, they are different. Okay? So let's actually continue with more of such relations. For instance, how would you define that a person is an uncle to another person? And let's see if anyone can actually respond to this question. So X is an uncle to Y if anyone? There are actually different ways. So if it's a sibling of a parent, and that sibling must be a male, so male X to Y, male X, and it's a sibling X to some Z, and Z is a parent of Y. That is an uncle. Basically it's a male sibling of a parent. Okay? Cousin, we all had it. So cousin X to Y if, and now we basically can say that they both have a parent and those parents are siblings. So if X has a parent that is Z and Y has a parent that is T, and they are siblings, Z to T. So we are actually not even interested in basically the who are the actual parents. So Z and T are not actually represented in the answer when we actually query the system. So let's save it at this point and load it again in Prolog. So in AccessBeProlog, I'm going to consult family, and we can ask who are the cousins. So X is a cousin to Y if and it tells me that in my database, in fact, I have no cousins. Basically, my database is too small to have any cousins in this database, which is in fact true, because if Liz would have a child, that child would be a cousin to Anne and Pat, but otherwise I don't have cousins in my database. So let's actually create a cousin. This way we actually can test that predicate. So parent Liz to Paul, and we reload the database and we ask who are the cousins, and now we can see that Paul and Anne are cousins and Pat and Paul are cousins. And of course we get all the possible orderings, because now it will actually backtrack, and we'll see what backtracking means. It will backtrack and find other answers. Now in AccessBeProlog and in most Prolog systems, there is also a way to debug programs. It's called tracing. So for instance, we want to trace a predicate like mother x to y. Tracing means that start executing that predicate step by step. It's like we are doing debugging in Java or any other programming language. So in this case it says this variable, it's the internal representation of x, is a mother to this variable if it's a parent of x to y, of that variable to the other variable, and it will find that Pam is a parent to Bob, and then if Pam is a female. So it basically executes the rule step by step, and it returns answers. Now when we press semicolon, it actually backtracks. It says redo the previous predicate, and in this case it basically asks, can you redo Pam as a female? No. Then redo the parent, and it gives me more parents like Bob to Anne, and it checks if Bob is a female. That fails. Then we'll ask for other parents. Tom is a female, fails. And this basically backtracks to the database and finds other mothers to children. When we want to stop tracing, we can write no trace as a query, and now the program is basically not tracing. If we re-ask the query, it will basically give us the answers, as many as we want. Okay? Okay, so any questions? No. Let's continue with the lecture. So what about if we want actually to write a recursion? Basically, we want to find all the possible ancestors of a person in our database. So if we return back to our graph, like for instance, the ancestors of Jim includes the parent of Jim, the grandparents of Jim, the great-grandparents of Jim, and so on, but there is no limit of how many ancestors a person can have. So we cannot write it as a rule like we have for grandparent, which has 2 steps. We have to write unlimited number of steps for finding all the possible ancestors of a person. Now, in fact, this also would work by detecting what are all the possible descendants of a person. Because again, if we start with the first argument bound, then it will find the children, grandchildren, great-grandchildren, great-great-grandchildren, and so on. So in rules we can also do recursion. We can say that x is an ancestor to y if x is a parent to y, so it's a direct parent, or if x is an ancestor to y if x is an ancestor to, it's a parent to z, and z is an ancestor to y. One thing that you notice that I wrote in this program is the fact that I'm using right recursion. So basically when I'm asking a query like who is x an ancestor to y, I'm not asking the next query is z an ancestor to y, because if these two are free variables, this will be the same query as before, which actually will lead to an infinite loop, and we will never get an answer. Basically, it will always ask the same query again. So as I said earlier, it matters when we try to write programs that we have the base cases first, and then we use right recursion. It will give us the correct answers first, and then it will try to do recursion. So again, let's try to write this program in AccessBeProlog. So we've wrote a couple of programs before. Now we had also grandparent. So we said that x is a grandparent to y if x is a parent to some z and z is a parent to y. But this will give us only one grandparent, only the grandparents, only one ancestor, the ones that are grandparents. But now we can write basically the recursive version, which basically asks for all the possible ancestors for a person. So ancestor x to y, first the base case. So the base case basically said that if x is a parent to y, or ancestor x to y if x is a parent to some z and ancestor z to y. So now we have recursion. Basically, if we are asking in Prolog, and again we have to load the program before we run a query, who are the ancestors of whom, it will first give us the parents. Basically, Pam is the parent of Bob, Bob is the parent of Anne, and so on. These are all the direct parents. But after this, it will start giving us grandparents. Like for instance, Pam is a grandparent to Anne, Pam is also a grandparent to Pat. And this will continue to great grandparents. So basically it finds all the possible ancestors of every person, every possible person. But the power of Prolog actually also stands in the fact that we don't always have to ask queries or questions with free variables. We can ask directly with bound variables, like is Bob an ancestor to Pat? And that will basically tell us yes. If we're asking who are all the descendants of Bob, it will give us all the possible descendants of Bob. But in the same way, we can ask who are all the ancestors of Anne, and it will give us all the possible ancestors of Anne. So the power of Prolog stands in the fact that it's a theorem prover, and we'll see what we mean by that. It's basically you can pass any argument, bound or variable, and it will try to prove if it's true, and if there are variables in that specific query, it will also give you what are the values for those variables that makes it true. Okay? But this, until now, we only had basically how to write simple programs in Prolog. Okay? And you can get easily into cycles. And there is actually a famous song in a classical song in US, I'm My Old Grandpa. You can actually listen to it on YouTube if you want. It's a very funny song. But it's very easy to run into infinite loops. Like for instance, if you write the previous program in this format, which basically uses ancestor as left recursive relation, you can see that if you ask a query like who are all the ancestors of whom, it will never return an answer. And the reason why is that it's an infinite loop. Basically, you are asking the query that will ask, and you can see through tracing the same query again and again and again and again and so on to infinity. So you will never get an answer. You will basically wait forever. So how does Prolog do computations? Like for instance, our original rule that x is a mother to y if x is a parent to y and x is a female. So first we ask that a query, like for instance, who is the mother of Bob? And that will actually replace the goal that we had before, the query that we had before, with the body of the rule. We can prove that M is a mother to Bob if we can prove that M is a parent to Bob and M is a female. So we basically solve the goal by solving, we solve the conclusion of this rule if we solve the premise of this rule. So now we basically ask a query where basically X and Y are bound to M and Bob, and who are the parents of Bob? Pam is a parent of Bob, and then we are asking the rest of the query, is Pam a female? And the system will respond true. That is true. Pam was the variable that was missing in this query, and Pam is a female. If we ask a similar query for Fodor, Fodor is written in a similar way, only that we query for males instead of females. So for the same query, for a similar query, what is the father of Bob? It will ask who is a parent of Bob that is a male. First, it will solve the left-hand side. This is in the order of Prolog, not logic. So Prolog will try to find parents of Bob. In this case, the first parent that it will find in the database of Bob is Pam. So again, it uses the order of the facts in the database. And then it will ask, is Pam a male? And that will fail. So that will backtrack and try to solve this goal again for another parent of Bob, and that is Tom. Tom is a male, and the system will succeed by giving us the answer that M is equal with Tom. And this is exactly what tracing does, and we saw it a couple of minutes ago in Prolog. So how does Prolog work? And we saw during tracing that basically we call a predicate. If that predicate is solved, it returns an answer to the caller. So we exit that query, and that's exactly what we did in the tracing that we had before. I will show it to you from the beginning. We called mother, mother called parent. Parent succeeded, and exit basically returns an answer, and or it fails, in which case it returns to the caller with no answer, like we had in the case of is Bob a male, and it failed. And then you will try the next spot to find an answer. So that will redo the another query, basically the previous query, to find an answer. Okay. So Prolog execution basically is very simple. It tries to solve a query by solving the bodies of rules that matched with that query. If it finds an answer, it returns the answer. If it doesn't find, it fails and returns to the caller, in this case the previous query, and it tries to redo, trying to in the next part to find an answer. Now, if you want, you can use the AccessBeProlog, but as I said, I'm using standard Prolog. You can download AccessBeProlog from this website, accessb.sourceforge.net. It was developed at Stony Brook University by David Warren, Michael Kiefer, Ciara Ramakrishnan, Ivy Ramakrishnan, Annie Liu, and many other people, Terry Swift, and so on. Myself, and so on. The installation is very simple. Unzip or untar the file that you basically download from Piazza. On Windows, you are basically done. You can add that path to your path environment variable, and you can execute AccessBeProlog. On Linux, if you download the sources, you can change to the build directory, configure, which basically will configure will find the C compiler and so on, and then make AccessB, which basically builds the AccessBeProlog, and that's it. Then now you have an executable added to the path and so on. On Cygwin, it's the same with Linux. You basically compile it with GCC on Cygwin or MIGW. So how do we use AccessB? Again, the same way that we did it before. Create a file with the extension PL or .p, open it in your favorite IDE or favorite text editor like Emacs, Notepad++, Vim, and so on, Atom, Sublime, and so on. Write your rules and facts, and don't forget all the rules and facts end with a period. You can use comments like you have in programming languages for paragraph comments. They start with the /* and end with */. or line commands which start with the %. It acts in a similar way with the // in Java and C++. And then you type accessb, the executable, or wherever it's located on your file system, and you will see a prompt. So now the system is ready to be queried. First thing that you will do is to load the program. So if your program was myprolog.p or .pl, you can load it with the file name within brackets. You can also load it with consult, and the file name can be complete given within single quotes, which is basically an atom in Prolog. Now the system is ready to be queried. So you can write queries like in the previous example. We can ask for what values of x, p of x is true. And again, the way that it works, it calls q of x and underscore, which basically is an anonymous variable. We are interested on those values of x, for which x is the first argument of q. And it will succeed for 1, x equal 1, x equal 2, x equal b. The good part about Prolog is that you have it's untyped. It's probably the weakest typed language. Last time we talked about data types. This is a programming language that basically has very weak types. You have numbers, any kind of numbers, atoms, which are basically strings within single quotes or that start with lowercase letters and they contain only letters, digits, and underscore. And you have variables and structures. We'll see what those are in a couple of minutes. So you can ask queries and the system will respond back with answers. Like it will give you values of x, or it will confirm if p of 1 is provable or not. Some useful build-ins are writex, which basically writes the value of x, writeln, which puts new line after the value of x, nl, which actually outputs the new line, equal for checking if two variables or two structures are equal, inequality, which we saw earlier. A useful trick, if you want to find all the possible answers for a query, is basically the system will only give you the first answer. You can type semicolon and then it gives you other answers. The moment that you stop typing semicolon, it will actually just respond yes. Typing semicolon is tedious. To do it programmatically, you can actually fail explicitly. So basically in this case we are asking q of x and write the value of x followed by an explicit fail, which backtracks and finds other values of q of x for which we basically get good answers. Okay? So let's actually come to our example. So in our example, we can ask a query like who are all the ancestors of n. We can query them all with the semicolon, or we can write the ancestor, write the fact that x is equal, and then we can use write the value of x, and let's put a new line and explicitly fail. And then if we want to succeed at the end of this query, we can also succeed at the end. So basically now it writes all the possible answers and then succeeds to that query. Okay? We can also do the same with find all. So we can ask find all x's such that ancestor x to n in a list L, and that will give me the list L contains now all the possible ancestors of x of n. Find all, there is also set off, bag off, which returns basically a set instead of just a bag of all the possible values. We will see them later. Basically find all takes as the first parameter is the pattern that we are looking for, in this case just x. The second one is the query that we will collect all the possible answers, and the third parameter is the list of answers that we get. So it basically collects all the x's from ancestor of x to n into the list L, and that gives us the list that we had here. Okay. Any questions? Okay, so one question is that one student says that it doesn't recognize files. Usually what happens, and I tell you that by default in Windows you do not see extensions. So when you create a file, especially a text file, you get an extra extension .txt. So in that case, if you try to actually load the file in Prolog, you will not be able to load it with just family because it has an extra parameter, an extra extension. And in this case, you will use .pl.txt. I mean, the file with the correct file name is .txt. So it basically loaded that file with the extension that I gave it. And in this case, it also found some issues in the file. I'm redefining the parent, the relationships that were defined before in .pl. But my point is that you have to be very careful what is your full file name in your system. So you can find out, even if you don't see the extension txt, you can look at the properties of the file and see the entire extension that this is a txt file. So you have to change the extension. So I think that would respond to your question that on Windows you don't see the correct extension. At least that's what I think that your question, AccessB on Windows doesn't recognize. Okay. Are you sure that you are in the correct directory? If you halt AccessB and you run dir, does it show your file with the correct extension? No, not necessarily. Because of the fact that I added it to the path, I can run AccessB in any possible directory. So again, basically what you can do is, if you're on Windows, open for your this PC the properties, advanced settings, environment variables. Either take the path in your variables or the path in the global and add with new the path to AccessBeProlog. Okay. So you have to, in that way you can run AccessB anywhere on your system, including on the desktop. So you can exit AccessB with halt. If you can't run AccessB, that basically means that you don't have it in your path, environment path variable. It's very easy to add to your path. Either follow the video that I will post or just query on Google how to add paths to your path environment variable in Windows 10 or in Windows 7 or in Windows XP or whatever operating system you have. And then you will be able to run AccessB anywhere you want. I posted an example how I did it on in my system on Piazza. Okay, so I think that will solve that problem. Okay, so let's start with logic programming concepts. So in logic, most statements can be written in many ways. In fact, when you took CSE307, you wrote many different statements, universally existentially quantified statements and so on. That's great for people, but it's a nuisance for computers and automatic proving. So it turns out that you can make small restrictions on the format of statements so you can prove theorems mechanically. And most common restriction is to have a single conclusion implied by a conjunction of premises. And these are called Horn clauses. They were named after a logician, Alfred Horn, who first pointed their significance in 1951. And that's exactly what logic programming does. Basically, we state all the statements as a a fact implied by a conjunction of premises. And the variables in that rule are universally quantified outside the rule. And this is the guy that invented or basically came up with this type of programming that is very easy to solve, or relatively easy to solve, with mechanical or automatic theorem proving, Alfred Horn. So the operators that we have in logic programming are conjunction. We can also write rules with disjunction. So instead of stating basically rules with just conjunction or multiple rules, we can actually use disjunction or semicolon. Negation, which basically we can state that some facts are not true in the body of the rule, and implication. Universal and existential quantifiers, that's also something that we have in logic. And then statements are sometimes true, sometimes false, sometimes unknown in systems that have three-valued logics, basically three true values. Axioms are facts that are assumed true, theorems are provably true, and goals are things that we would like to prove true. A prolog program is a sequence of clauses. Each clause, sometimes called a rule or a Horn rule, as we said before, is of the form head, heave, body. The head is one term, and the body is a comma-separated list of terms, which is in fact a conjunction. If the body is empty, then you basically can just write head followed by period, which is called a fact. That's an axiom. It states that the head is implied by true. That means that it's always true. So the prolog interpreter has a collection of facts and rules. And the facts are those clauses with empty bodies, like raining in New York or raining in Seattle. Then facts are axioms. They are things that the interpreter assumes to be true. The prolog will provide an automatic way to deduce true results from facts and rules. A rule is a clause with both sides. Basically, it has a head and a body. The body could be one fact or a conjunction of facts. So a rule that in this case may be true is the fact that if it's raining in some place, then it's wet in that place. So if it's raining, for instance, in New York and Seattle, then we basically find out that also it's wet in New York and Seattle. So the meaning of the rule is that the conjunction of the structures in the body implies the head. So if we find all the facts in the body to be provable true, then the head is also provable true. Now, in logic, all the variables that occur in the body of a rule are single assignment variables. That means that they must have a single value for the entire rule. That means that if we have multiple queries in the body, X means the same thing in all of these queries, and it will be also bound for the head of the rule. So we can also write clauses where you basically have a query. In this case, where is it wet? It only has a query. It basically responds what are all the places where we can prove that it's wet. So rules are theorems that allow the interpreter to infer things. To be interesting, rules also contain variables. So for instance, in this case, employed X if there exists a Y such that X is employed by Y. So this can be read for all X. I want to find all of the X's that are employed, where X is employed if there exists a Y such that that Y employs X. So notice the fact that this implication is from right to left. So the right side is the premise and the left side is the conclusion of this rule. It basically says if we can prove the right side or the body, then we can prove the head. Also, it doesn't say that X is employed only if Y employs X. There can be other ways to basically find that X is employed. So, for instance, there can be people that are self-employed, like employed Bill, or people that we don't know who's employing them. We know that Bill is employed, but we don't know who is in the employer of Bill. And employed X if X is self-employed. So the rule really uses if. That means that if this is true, then it implies this, but it's not only if. Basically, it's not always the case that employed only if somebody else employs X. So it's just one way to prove the head of the rule. You can actually consider that all the rules that contain as the head the same head are basically can be proved from all the bodies for those rules. So the scope of the variable in the clause in which appears is the following. For the variables that occur on the left-hand side in the query in the head, they have implicit universal quantifiers. We basically want to find all the possible x's that are employed in that previous rule. So this rule is basically for all possible x's. X are employed if we can find who employs them. Variables whose first appearance is in the body of the clause are existentially quantified in that body. So for instance, there exists some y that employs x in our rule. Note that these variables are also universally quantified outside the rule, and you can actually build the logical equivalencies that this is employs y, x implies employed x is logical equivalent with a disjunction that has the body of this rule as a negation, and the negation applied to existential quantifier transforms it into universally quantified variable outside the rule. So it is true that basically all the variables are universally quantified outside the rule, but by intuition, when we actually read the rule, the variables that occur in the head are universally quantified, and the variables that occur only in the body, like y in this case, are existentially quantified in that body. That's why when we read it, we actually have an existential quantifier. We say that x is employed if there exists a y such that y employs x. Okay, so let's see another example. We said that we can show that there are multiple rules to prove grandmother. So grandmother A is a grandmother of C. If A is the mother of some B and B is the mother of C, so we basically say that for all A and C's, A is the grandmother of C if there exists a B such that A is the mother of B and B is the mother of C. We probably want another rule that says that a mother of B, if B is a father of C, is also a grandmother. This is the paternal grandmother, this is the maternal grandmother. So again, we basically quantify all the variables that occur in the head of the rule universally, and all the variables that occur for the first time in the body of the rule, like B, existentially quantified in that body. Now, transitive closure. For instance, we have a graph defined with a set of facts, true statements, like there is an edge from 1 to 2, there is an edge from 2 to 3, there is an edge from 2 to 4. Now we can actually write reachability. So if there is an edge from x to y, then we can reach y from x. We can write it as we can reach from x, y if there is an edge from x to y. Also, in reachability, we know that we can reach from x, y if there is an edge from x to z, and we can reach from z, y. This is the most general algorithm for showing reachability. Basically, either that we do it breadth first search and we look at the neighbors, and from those neighbors we try to find the path to a given node, or we actually do depth first search. This is exactly the same. Basically, we look at the neighbor, and then from that neighbor we look at its neighbors, and so on until we reach the node that we want to reach. But two things that we can observe in this case is the fact that we have the base case first, and then that the recursive case is written with right recursion. And for the reason for that, we will see later, is in the order of actually trying to prove this in Prolog, which is kind of depth first search with backtracking. And here is an example. In the same graph that we had before, there is an edge from 1 to 2 and from 2 to 3 and 2 to 4. And the program that we had, if we are asking what are all the nodes reachable from other nodes, like what are all the y's reachable from x, it will actually reply first with the edges. Basically there is an edge from 1 to 2, then there is an edge from 2 to 3 and 2 to 4. So 2 is reachable from 1, 3 is reachable from 2, and 4 is reachable from 2. And then it will start giving us longer paths that we can reach from 1, 3 and from 1, 4. And those are all the possible reach xy that we can find in this graph. If we have cycles, it will actually give us infinite number of results. Basically, it will give us multiple times that we can reach certain nodes. So we'll now explore in more detail how Prolog actually, the syntax of Prolog and then the semantics of Prolog. So the terms that occur either in facts or in rules are either, as we can see in this case, atomic. They are numbers or they are strings, like we had in the case of Bill in this case. Or we can have structures, and structures also include lists. So we'll start with the possible terms that can occur in Prolog. And terms can be atomic data, variables, and structures. That's why I said that Prolog is very, very weakly typed. Basically, it doesn't have any kind of like precision. Internally does. It will detect if numbers are integers or they are reals. But for the user, numbers are numbers. And that's it. You don't type any variable, you don't type constants and anything like that. So atomic data can be numeric constants like integer, floats, like 1024, minus 42, 3, period, 1415, 6, period, 0, 2, 3, exponent of 23, and so on. Any numbers that you have in a programming language like Java or C or Python will be recognized in Prolog. Atoms are identifiers, are sequences of letters, digits, and underscore, beginning with a lowercase letter. Like for instance, Paul, R2D2, 1 underscore element, these are all atoms. Also, strings of characters enclosed within single quotes. Like for instance, if you want to have as a string Stony Brook with a space, you have to enclose it within single quotes. Because in identifiers you cannot have spaces. But within single quotes you can basically have anything. Period, space, and so on. Variables. Variables are identifiers that begin with an uppercase letter like X or index, or underscore like underscore parameter or param. These are single assignment logical variables. That means that in a rule a variable can only be assigned once the rule execution, and different occurrences of the same variable in the same clause denote the same data. Variables are implicitly declared upon their first use, like for instance reach x, y. Variables are not typed. We don't have types in Prolog. Basically the types are discovered implicitly. There are no declarations in logic programming for variables. That's not actually true. There are no declarations in Prolog. There are all kinds of logic programming systems that may allow some declarations, but not in standard Prolog. If variables do not start with an underscore, it's assumed that they appear multiple times in a rule. So if a variable doesn't appear multiple times, then a warning is produced, like singleton variable. And you can use variables preceded with underscore to eliminate this warning. So your question may be, why do we actually need this kind of like underscore? The reason is that we don't have types. So in order to make sure that a user did not mistype a certain variable name, like he didn't use index and then mistyped index in another position, it's a signal. Warnings are not errors. They are basically just signals to state to the user that you may have some issues in your program. In order to actually make sure that your program is correct, I would recommend, actually require, that you actually eliminate all the possible warnings in the program using anonymous variables. They are also called don't care variables. Basically, they are variables that start with underscore. Underscore by itself represents such a variable. Each occurrence of underscore corresponds to a different variable. Even within a clause, underscore does not stand for the same object. A variable whose name begins with underscore but has more characters like underscore radius or underscore size, they are don't care variables. That means that we give it a descriptive name because we are programmers and we want to identify the fact that they mean radius or they mean size, but they basically are used for creating relationships within a clause, but we don't care about the answer, the result for that variable in the output. So warnings are used to identify bugs, mostly because of copy-paste errors, and they are used instead of declarations of types and type checking in logic programming. Again, my advice is fix all the warnings in your program so you know that you don't miss any logical error. So what exactly I mean by that? Let's return to our Prolog program, and I'm going to create a new file on the desktop. Let's call it test.pl. I'm going to open it with Notepad++, and we are going to write the previous rule that we said, that employed X if there exists some Y that employs X. And as I said, I prefer to actually always write one atom, one predicate per line, so I will actually write it in this way. And let's assume that there are multiple employees relationships, like employees Bob, Pam, also employees Paul, Tom, also employs, maybe Bob also employs Peter, and Bob also employs Anne, and Bob also employs Pat. And there are multiple ways to have employed. So maybe we know about Bill being employed, but we don't know who employs him. We also may actually have people that are self-employed, like employed X if self-employed X. And let's say that Larry Edison is employed, so self-employed Larry, and also self-employed Mark. Okay, so now when we compile this file, so I start AccessBeProlog and I compile the test program. Oops. I get a warning, and that warning is that there is a singleton variable Y in the clause for employed. So then I come back here and I see, yes, that is true. Y is a variable that only occurs once in employed, and I don't care about its value because I only care about who is employed. So I precede Y with an underscore. Or I can even delete y completely. So now when I compile again test, there is no more warning. So my advice is to actually, all the variables that you only use once, like for instance I did here, they should be basically just in one clause, they should be anonymous variables. Okay? Any questions? So in this case I can actually, let's see who are all the people that are employed. Find all x employed x into a list L. And it gave me that Pam, Tom, Peter, Anne, Pat, Bill, Larry, and Mark are employed in different ways. It's either that they are self-employed, or they are employed by other people, or they are employed but we don't know who is the employer. Okay? Any questions? Okay, good. Variables, we said 3 times until now, but let's actually say it again. Variables can be assigned once. They are single assignment, but they can further be refined. Like for instance, x can be assigned f of y can be assigned g of z later, and z can be assigned 2. And when we run such a query in Prolog, it will actually respond that x is f of g of 2, because f was that x was f of g of 2 by initializing y later and z later, and y is g of 2 and z is 2. Even the order, because of the fact that Prolog is a conjunction, this query is a conjunction, basically we have, we can say that z is 2 and then f is y and y is g of z. And we can see that x will be f of the value of y, where with y was g of the value of z, so it's again succeeds with the same. Even infinite structures. For instance, if x is f of x, this is true if x can be replaced now in the definition of x, so we basically have that x is f of x, and again we can replace x with f of x, and we will respond that x is f of infinite structure. You can think about this as pointers. Basically what this says is that x is a value that is f of a pointer back to x itself. So basically we have f of a pointer to f of a pointer to f of a pointer to f, and so on. So it's like everything is reference based variables. We talked about references last time when we talk about data types. Okay? So in order to run a Prolog program, one would ask the interpreter a question. This is done by asking a question to the program, and if it can prove it, it will respond yes. If it cannot, it will respond no. If your question contains variables, then the interpreter will print those values and give them to you. That makes basically those values for which the query becomes true. So in the previous examples that we wrote lots of examples. You can ask, where is it wet? Or is it wet in New York? If you are asking, like, is it wet in New York, it will respond yes. If you are asking, is it wet in a place that is not wet, then it will respond no. If you are asking, what are all the x's where it's wet, it will respond New York, Seattle, and no other places, based on the rules, the facts that you have in the database, and the facts that you have in the database. Similarly, here I give reachability, and as opposed to the previous query where we had all the variables free or bound, you can have in reachability some variable bound, some variables free, and you can mix them. You can ask a query like, is D reachable from A, or what are all the nodes D, what are all the nodes that can reach D, what are all the nodes reachable from A, can we reach from DA, and that will respond no in our graph, and what are all the nodes that are reachable from other nodes, in which case it will give us tuples. It will tell us what are all the x's together with y's that are basically reachable. So until now we talked about practical aspects of Prolog, but we have to understand what is actually, why is it logic. And the reason why is that there are two meanings of prolog. There is the model theory, which is called the declarative meaning, which is what are all the logical consequences of this logic program. And there is the procedural meaning, for which values of variables in the query I can prove the query. So the user gives to the system a goal, and the system will try to attempt to find axioms and inference rules to prove that goal. If the goal contains variables, then also gives the values to those variables for which the goal is proven. Now, the procedural meaning computes answers that are true that are logical consequences of the program. So basically the procedural meaning is sound and in some cases complete with respect to the declarative meaning. Sound means that it will only prove queries that are logical consequences of the program, and complete would mean that it will compute all the possible answers to the program. Now the problem is that it doesn't always compute in finite time all the possible answers to the program, but that is usually because of the fact that we basically can write programs that have infinite loops. But first we have to understand what is declarative meaning of logic and what is the procedural meaning. You may already know these two terms, the declarative versus the procedural meaning, from classes like Foundations of Computer Science or Mathematical Logic. But today we have to do that in this context of programming languages. So the declarative meaning, we'll take an example and explain exactly on this example what is the declarative meaning of a program. So my example is very simple. Basically, we have a set of facts that are true, that a bear is brown, a bear is big, an elephant is gray, an elephant is big, a cat is black, and a cat is small. Then we have a bunch of rules that Z is a dark thing if Z is black, or Z is a dark thing if Z is brown, and X is dangerous if X is both dark and big at the same time. So the logical consequences of the program L is defined as the smallest set of relations such that all the facts in the program are in all the axioms in the program are in L. And if we have a rule that basically states that the head H is true if the body B1, B2 up to Bn are true, is a clause, an instance clause of the program such that all the bodies are in the set L, then the head is also in the set L. So in addition to the facts that we get in the previous program, that smallest set of logical consequences of the program also includes the fact that because a cat was black is also a dark thing, and because a bear is brown is also a dark thing, and then it also has that a bear is dangerous. It's dark and big, and is the only other thing in addition to the facts in the program. So if the logical consequences of the program is basically a set of relations. In our case, that set of relations are all the facts together with these three additional facts. So, in fact, I should probably just write it down explicitly. So let me take a moment to do that. So the logical consequences L of this program is the set, and that set should contain all the facts. And in addition to those facts, also dark cat, dark bear, and dangerous bear. So let me actually write it down. So bear brown, big bear, gray elephant, big elephant, black cat, small cat, dark cat, dark bear, and dangerous bear. This is the set of logical consequences of the program. This and nothing else. Basically, this is the complete set of logical consequences of this program. Nothing else in addition to this. Let's make it a little bit smaller. So this is all that can be proven as logical consequence of this program. Okay? The smallest set such that all the facts in the program are in L, and for every instance clause of this program, if the body of that is in the set, then also the head of the head of the clause is in the set. And all the facts are in L. Basically, those are all the things that are true by default. Okay? This is the declarative meaning, also called the model theory. Then we have the procedural meaning of Prolog. Basically, a goal and a query in general is a conjunction of goals. We want to prove that G1 and G2 up to Gn is true. In order to prove that query, we select a goal, G1, that's the order of goals in Prolog, and we find a rule such that G1 and H are matched. That basically means that we try to match the goal and the head, and we replace the variables in the head with the variables in the goal. Under the substitution of all the variables, now we have to prove that B1 to BK, basically the body instead of the G1, is true, followed by the rest of the goals. If nothing else is left to prove, because we may have facts which have an empty body, then the proof succeeds. If there are more clauses to match, then the proof fails. So, let's actually do an example, and that we understand. We want to prove dangerous Q. So, in that case, we basically try to find a rule where dangerous is the head of the rule. So we select dangerous X if dangerous X and big X, and instead of, we replace the goal with the body of the rule. Exactly what we did in the previous case. We replace G1 with the body of the rule, and we prove again the goal. So we can prove dangerous Q if we can prove dark Q and big Q. If we can prove those, then we can also prove dangerous for the same variable Q. Now we will start with dark Q. So dark Q, we again find all the rules that we have dark Q. Dark Q will select the first clause of dark, which is dark Z if black Z. And now we replace dark Q with black Q. And we have a new goal, which is black Q and big Q. Now we will select the only fact that is black in our database, which is black cat. And we'll basically, that does not have a body, so we have it true. And now we have big cat, which actually fails, because we have only two facts in the database, big bear and big elephant, and cat does not unify with bear and elephant. So this proof fails, and then we go back to dark Q, back to step 2, and we select the second clause of dark, which is dark Z if brown Z. And now we try to prove brown Q, big Q. The body of, basically we replaced dark Q with brown Q, and we added it to the query. We still have the same query to prove brown Q, big Q. So now we continue the proof for dangerous Q. We select that brown Q solves with brown bear, and we want to prove now big bear. Big bear succeeds because it's a fact, there is nothing left to be proved, so the proof succeeds. And we get the answer that Q is equal with bare. Okay. So in fact we can build this tree of search. We wanted to prove dangerous Q. Dangerous Q was true if dark Q big Q, so we replace dangerous Q with dangerous Q and big Q. Dangerous Q can be solved in two ways. So dangerous Q if it's black or dangerous Q if it's brown. We choose the first way in the order of rules, clauses in the database. So we try to prove black Q big Q. Black Q succeeds for black cat, in which case we are left to prove big cat, which cannot be proved. We fail. We backtrack the search tree, and now there is nothing else to be black. If there was something else to be black, then we would have another branch here. But since there is nothing else, we backtrack more and we find other clauses to solve dark Q. And dark Q is true if brown Q, which will replace the head dark Q with brown Q. Brown Q and big Q succeeds with brown Q, brown bear. And now we want to prove big bear. Big bear was a fact and it succeeds. Now if we actually press semicolon, it will backtrack and try to find other things that are brown. And if that fails, it will backtrack and finds other rules that define dark. If that fails, it backtracks to find other things that are dangerous, and there are no more rules, so it will tell us that this is the only answer possible. Okay? And this is the procedural meaning of Prolog. It's a depth-first search with backtracking. If you think about it, it is exactly what, like for instance, search in a graph, the algorithms that you learned in algorithms are doing with backtracking. Any questions? Okay. So Prolog interpreter works with what is called backward chaining. Basically, it's a goal-directed top-down proof system resolution. It begins with the thing that it tries to prove and works backwards, looking for things that would imply it, until it gets to facts, and that basically proves the original goal. It is also possible to work forward from the facts and trying to see what other things can be proved to be true if we are looking basically for the rules. This kind of methodology is called bottom-up resolution, and it's very time-consuming because you start with the facts. Like in this case, you would start with the facts, and then you will look at the rules and see, oh, from the fact that a cat is black, I can prove that a cat is dark. From the fact that a bear is brown, I can prove that a bear is dark, and then I can prove that a bear is dangerous. These kind of proof systems are called bottom-up resolution. From the facts, you can infer everything that is true in the system. And you stop in the moment that you reach a fixed point. Nothing else can be proved to be true. This kind of approach is adopted by other logic programming systems like answer set programming paradigm. You can search about that on Google and Wikipedia. DLV, Potasco, OntoBroker, and so on. Fancier logic programming languages use both kinds of chaining, basically with bottom-up resolution and top-down resolution in certain cases. And in fact, AccessBeProlog is such a system. It uses what is called tabling, which is not an ISO prolog, so we are not going to go into it. But if you want to know more details about this kind of proof systems that match procedural meaning to the declarative meaning of logic programming, you can take CSE307, which is a graduate course on computing with logic. But let's return to Prolog. So when it attempts to do resolution, a Prolog interpreter pushes the current goal into a stack, makes the first term of the body, in the body, the current goal, and goes back to the beginning of the database and starts looking again. If it gets to the first goal of the body successfully, the interpreter goes to the next one. If it gets all the way to the body, then the goal is satisfied and backs up one level and proceeds. Basically, it uses a stack to actually implement logic inference. So again, the procedural meaning of Prolog begins at the beginning of the database. This is part of the order of Prolog, not logic programming in general. It looks for something which unifies with the current goal. If it finds a fact, then great, it succeeds. If it finds a rule, then it attempts to satisfy the terms in the body of the rule, depth first search, again, left to right. And this process was motivated by the resolution principle due to Alan Robinson in 1965, which you can see on the left corner, which basically said that if C1 and C2 are two Horn clauses and C1 represents a true statement and the head of C2 unifies with one term in the body of C1, then you can replace that term in C1 with the body of C2 in order to obtain another statement that is true if and only if C1 is true. So if it fails to satisfy the terms in the body of a rule, then it has to undo any unification of variables in the left hand side. This is backtracking. And this uninstantiates any variable that was given a value as the result of unification and keeps looking through the database for something else which will unify. So it basically backtracks one level and tries again. If the interpreter gets to the end of the database without succeeding, then it backs out one level, or it may fail to satisfy something in the body and continues from there. It finds another rule to prove the previous level. But you see two differences between what we described about Prolog and procedural meaning. The fact that Prolog is not purely declarative. The ordering of the database and the left to right pursuit of sub-goals gives a deterministic imperative semantics to searching and backtracking. Basically, changing the order of statements in the database would either lead, in some cases, to infinite loops or can result in inefficiency because you recompute goals that you already saw before. And the example of an infinite loop is basically the reachability written this way that we see below. Is left reachability, we basically say that we can reach from xy if we can reach from xz and there is an edge from z to y. Or we can reach from xy if there is a direct edge from x to y. And if you are asking a query with two variables that are free, like reach xa to b, that's an infinite loop, because it will try to prove this by using the first body of the first rule about reach, and the first goal that we see there is also a reach with two variables. So basically this procedural meaning of Prolog, which always starts in the database from top to bottom and in rules from left to right, it will basically result into an infinite loop. But this is a problem of programming. So if we program rules correctly in a right recursive fashion and facts first, then we will get results correctly. Okay, any questions with what we learned up to now before we are getting into structures? Okay, good. So let's get into structures. Probably we should pause for 10 minutes. We are actually going for 2 hours now. And let's see, I never actually tried to pause. Okay, let's continue with the rest of the lecture. So we talked about data types that are allowed in Prolog, and we said that there are atomic data types, like for instance numbers and atoms, or identifiers, and variables, and then we have structures. So what exactly are structures? They are like pointer-based structures. If f is a functor symbol, like an identifier, and t1 up to tn are terms, then f of t1 up to tn is also a term. So it will be like a tree structure where f is the functor symbol and the arguments are given in order. If f is called, in that above structure, f is a functor or a functor name, and t of i's are called arguments. Structures are used to group together terms that are related, like for instance lists or trees. Basically a list, like in SML, is given by the head of the list and the rest of the list. So it's in fact a tree structure. And we can basically define any expression trees. Like for instance, if we want to represent a mathematical expression, we can represent it as plus of minus of number of 3, number 1, star of number 4 and number 2. Data structures may have variables, and the same variable occurring on multiple sites on multiple times in the data structure represents the same term. So what exactly are structures? Let's actually show an example. So when we write a term, like for instance x is assigned f of, let's say, 1. F of 1 is a structure. Basically, it's a way to compose multiple elements into one element. F of 1, 2 is also a structure. F of g of 1 and 2 is also a structure. So it's basically a way to represent trees. And this could be also an arithmetical expression, like plus between 1 and 2 is a structure. Plus between 1 and the product, so mult or star of 2, of 3 and 4 is also a structure, and so on. Now structures may also contain variables. So for instance, we can have here y as a variable and maybe y again in the product. So now it basically tells us that x is the plus of this variable and star of the same variable number and 4. Now structures can also be matched. So for instance, we can match plus of 1 and star of 1 and 4 with plus of y and star of y and 4. And we have the same variables occurring basically multiple times in the rule is bound to the same value. So for instance, if we have an x here, now will tell us that x and y are both 1. How? Because this 1 is matched with y, and then x is matched to y, and y was already matched to 1. So it must be the case that x here is also 1. So structures are basically a way to compose the arguments. You can think about structures as tuples, but with names. So in SML we had tuples. You can actually structure together 1 and 2 as a tuple. But in Prolog you can also give it a name. So this also works without basically as tuples in Prolog. But since Prolog is mostly about names, we can actually name the tuple of two arguments into a single under name. Okay, so data structures may have variables, and if a variable occurs multiple times in a data structure, it means the same term. Matching is the operation to find substitutions for variables in the two terms t1 and t2, such that it makes the two terms identical. And we will introduce later what is that called in logic, in the declarative semantics, where basically that has a logical semantics. So for instance, if we have the two structures matched with the equal symbol, it will tell us that the structure on the left hand side matches the structure on the right hand side if x is equal with 1 and y is equal with 4. Then the two structures are the same. Matching is actually an algorithm. We can match two terms. We can say that this term is matched equal with this other term if they match each other. And what does it exactly mean? It means that the constant can match each other. Like for instance in Prolog, if we say 42 matches 42, that is true. A constant matches another constant. A variable matches with anything, but if the variable occurs multiple times in a rule, it has to match the same value. So if it matches something other than a variable, then it instantiates. If it matches another variable, then the two variables become associated. Basically, the two variables are aliases to the same memory location. So, for instance, if we say A matches 35 and then A matches B, then B is also 35. This is not assignment, is actually matching. Is the fact that we actually unify those two structures into the same thing. That's why if we say that A matches B and then later we say that A matches 35, also B is now 35. So two structures match if they have the same functor, if they have the same arity, and if they match recursively. So for instance, foo of G of 42 and 37 matches foo of A and 37 if A matches G of 42, and we see that 37 matches 37. So this is a recursive algorithm. It basically says that two structures match if they have the same functor, the same arity. That means that we can match every argument with the corresponding argument in the other structure, and if they match recursively. So we have to dig down. Also, foo of G of 42 and 37 matches foo of G of A and B. Why? Because it's the same functor, they are both binary, and then G of 42 matches G of A because it's the same functor and A is a variable, it matches 42. So the general rule algorithm for matching of two terms is the following. If S and T are constants, then S and T matches if both are the same object, are the same constant. If S is a variable and T is anything, then T matches S. Basically, the variable is now bound to that value. If T is a variable and S is anything, then S matches T. That means that T is now bound to the value of S. If T and S are structures, then S matches T if S matches T have S and T have the same structure, the same functor, the same arity, and all of their corresponding arguments also match. So we basically have to look at the arguments if they match. So here are a few examples. For instance, the left hand side matches the right hand side if X matches 1 and Y matches 4. Otherwise, the functors are the same. Plus matches plus with arity of 2. Minus matches minus with arity of 2. Number 3 matches number 3. Number 1 matches number X if X matches 1. Star is a binary functor, the same on both sides. Number is a unary functor, the same on both sides. Y matches 4 if Y is now bound to 4. And 2 matches 2, so that's true. If we have the same variable and the variable matches two different values, like X matches 1 and 4 at the same time, then it will respond no. This structure does not match this structure because X cannot be bound at the same time to 1 and 4. So which one of these match? A being a variable matches anything else. Basically matches 100, matches functor of B, functor of 100, functor of CD, functor of plus of 99 and 1. Now 100 only matches A. Basically it's not the same with functor, so it doesn't match anything else. Functor of B is a unary functor, a functor with arity of 1 with one argument, so it will match functor of 100 by binding B to 100. It will also match A because A was a variable and A matches functor of B. So functor of B matches A, matches functor of 100, and since B is a variable, it also matches functor of plus 199 and 1. Functor of C and D, because it's a binary functor, can only match binary functors, so it doesn't match functor of B, functor of 100, and functor of plus, because this is also a single term, so it will not match a term with a functor with two arguments. So we have here all of the examples. So how do we actually access the arguments of a structure? We basically use matching. And if we only want a value, like if we want to get M, D, and Y, we can get M, D, and Y on the right hand side. So it will succeed with M, September, date 1, and year 2020. If we want only to get a day, then we basically use anonymous variables for the other positions in the structure. Lists. Prolog uses a special syntax for representing lists, but internally the list is actually also represented as a structure. Basically, a list is a structure using the dot functor. So the dot functor is basically a functor that is binary, takes the head of the list and the body of the list. The body could be the empty list, or it could be any other functor. Now, in order to represent the period, we have to put it within single quotes. So again, this would be the list that contains 1. At least it should be. Oh, did I do it? Yeah. It's not a query. We have to assign it. X is that. And then it's the list 1. So a list is represented like in SML earlier this semester as the head of the list and the tail of the list. So basically, if X is 1 and Y is 2, 3, 4 as a list, then the list that starts with the head X and the tail Y is the same with the list 1, 2, 3, 4. So the head is extracted out and the tail is extracted out. The empty list is represented by open close bracket or nil. It's an alias for empty list. The symbol vertical bar, also called pipe, is basically used for putting together the head of the list and the tail of the list. So you can use the notation for lists, either the list of elements or the list that has the head 1 and the tail 2, 3, 4, or the list that has the head 1 and the tail is a list that has the head 2 and the tail 3, 4, and so on. The advantage of Prolog is that you can enumerate multiple elements in the head. So you can also write the same list as the list that starts with 1 and 2 at the beginning of the list and the tail 3, 4. Or the list that starts with 1, 2, 3 and the tail 4. Or the list that contains 1 as the head and the tail is the list that contains 2 in the head, and the tail of that is the list that contains 3, 4 in various notations. So lists are actually structures. They are just syntactic sugar. That means that internally they are represented as this structure that is the period. The period that has as the first is a binary structure that has the head and the tail is the rest of the list. So we can also write the same list 1, 2, 3, 4 as the structure with functor period that has the head 1 and the tail is a list, basically a structure that has again the functor period and the head of that is 2 and so on. So there is another notation in Prolog that when we want to represent a functor with the number of arguments, we can represent it this way, the functor and the number of arguments. Strings are internally represented as lists of characters. So if you write, for instance, that X is A, B, C, this is just again a syntactic sugar that transforms that ABC is the list of character codes 97, 98, 99. And basically you deal with lists. So strings are not really strings. They are just characters surrounded by double quotes, which internally get translated into lists of characters, numeric codes. So now next is to actually program with lists. So how do we program with lists? The same way that we wrote in SML. We basically can write member, we can write append, we can write select, and so on. So let's actually remember how did we do it in SML. I'm going to use the same file that we had before. In SML you would write the function member, and you will say that X is a member of the empty list, should give us false, and then member X of a list that contains the head and the tail is if X is equal with the head, then we return true, else we ask recursively is if member of X in the tail. So this is how we wrote member in SML. This is in SML. Okay. Now how do we write it in Prolog? First of all, in Prolog, predicates that are not proved to be true are by default false. So the first rule that we had in Prolog, in SML, we don't have to write it in Prolog, because by default, if we are asking a query and that is not true, it's false. Then we write the second rule. So we said that if X was the head of a rule, then we should return true. So in Prolog, if X is a member of a list that starts with X and has a tail that we are not interested in, then it's true. So we wrote it as a fact. The first element of any list is a member of that list. We used, instead of the cons operator in SML, we used a pipe in Prolog, and the fact that this is a list. Next, member X of a list that contains any head. We are not interested in the head. Basically, if the head is not matches X but has a tail, is true if member of X in the tail. So this is exactly the second rule that we wrote in SML. X is a member of a list if X is a member of the tail. X is a member of a list that starts with anything and has a tail T if X is a member of the tail. So from SML to Prolog, there is not much difference. Basically, in SML we would ask queries like, is it true that 1 is a member of the list 1, 2, 3, or that 2 is a member of a list 1, 2, 3. And it will respond true in the first two cases. But you can also ask if 4 is a member of the list 1, 2, 3, and it will respond false in that case. So it will respond true, true, false. The same thing you would do in Prolog. Basically, if you ask the same queries for the program that we had above, but we finish with period instead of semicolon, it will respond yes, 1 is a member of 1, 2, 3 because it's the head of the list. 2 is a member of 1, 2, 3. In fact, it will use the second rule and you will say that if it's a member of the tail, and X is a member of 2, 3 of the tail because 2 is the head of that list, and 4 is a member of 1, 2, 3 does not actually, is not possible to prove, so it will respond false, is not true. Okay, what's the advantage of Prolog? The advantage of Prolog is that you can also write this query as member X of 1, 2, 3 And Prolog is a theorem prover. It will respond that yes, if x is 1, or if x is 2, or if x is 3, and no other cases. So the advantage of basically Prolog over SML is the fact that we can actually ask queries that contain variables, in which case it will use theorem prover through proving to find all the possible answers to that query, and it will tell us that there are no other possible answers. Okay. So Prolog is more basically powerful than SML. SML is a functional programming language. It's not basically more expressive, but it's more powerful in the fact that you can ask queries which have variables. In fact, you can even ask a query like member of 1 in a list X, and it will start responding that the list X could be a list that starts with 1 and has any possible tail, and if you are continuing asking, it will tell you that also a list that starts with any element but contains 1 as the second element is a list that contains 1, that a 1 is a member of, and this continues forever. Basically tells you that any list that contains 1 at any possible position, first, second, third, fourth, fifth, and so on, are basically lists in which 1 is a member of. Okay. So in this example, basically member 2 finds a given element in the list. The program is member X in the list that starts with X, or we can prove that X is a member of a list that starts with any element, one head, and the tail ys if X is a member of ys. And queries to this would be, is 2 an element in 1, 2, 3? Yes. What is X that is a member in list? It will respond X could be L or I or S or T and nothing else. If you are asking what f of X is member in this list that contains f of 1, g of 2, f of 3 and h of 4, it will respond that yes, I can prove this for x equal 1 or for x equal 3. It will not match f with g or f with h. And again, if you are asking what are the possible lists to which 1 is a member of, it will start enumerating possible lists that contain 1. The list that starts with 1, the list that contains 1 at the second position, and so on. So let's actually do it in Prolog. So we write the Prolog predicate, we consult the program that we had in the previous case in Prolog, which I believe I changed its name. Let's see, test.pl, it's the same name as before. So test, and now we can ask the queries. Is 1 a member of 1, 2, 3? Yes. Is 2 a member of 1, 2, 3? Yes. Is 4 a member of 1, 2, 3? No. What members for which axis can I prove member X in 1, 2, 3? And it will give me for 1, 2, 3 and nothing else. For which are the possible members of the list L, I, S, T, and it will respond with L, I, S, T. Those are the possible members of list. Similarly, we can ask what are the lists in which 1 is a member of, and it will respond the list that starts with 1, the list that contains 1 at the second position, the list that contains 1 in the third position, and so on. And the other things are anything, are variables. Basically, they can be anything, structures, strings, and so on. Okay. And this will give us an infinite number of results. Okay, so this is member. Another predicate is append. So append concatenates two lists in the form of the third list. So for instance, when we wrote it in SML, we said that appending the empty list with the list L is the list L. Appending a list that starts with the head X and the tail L with a list that is M is a list that starts with the head X and the tail N if appending the tail L with the list M gives us the list N. And this is written basically the same way. We can break up the first list into the head X and the tail L. Then we append L with M, the second list, and we get the result N recursively. And then appending XL, the list that starts with the head X and the tail L with M, gives us the list that starts with X and ends with the tail N. And we can ask queries to that. So actually, to make a parallel with SML, let's actually try to reason about it. So in SML, we wrote the append predicate as follows. We said that append, function append, because it takes inputs and outputs, inputs and returns outputs. So appending the list, an empty list with the list L is the list L, or appending a list that starts with the head H and the tail T with a list M is equal with a list that starts with the head H and finishes with a tail that is append of T and M. This is how we wrote it in SML. And then we ask questions like, what is the result of append of, let's say, 1, 2 with 3, 4. And SML will respond back with 1, 2, 3, 4. So now in Prolog, it's similar, only that arguments can be input and output arguments. So in Prolog we would write append of the empty list with any list L is the list L, and append of a list that starts with the head H and the tail T with the list L is a list that starts with the head H and the tail, let's say, T2, if T2 is the result of appending the tail T with the list L. The same query that we wrote in SML also runs in Prolog. Basically, calling append on 1, 2, and 3, 4 into a list L will succeed with the list L being bound to 1, 2, 3, 4. But we also have other queries that we can run in Prolog. In Prolog, we can also ask append of what list could have been appended with 3, 4 such that the result was 1, 2, 3, 4. And in fact, it will give us that, yes, I can prove that for the list 1, 2, for the list X that is 1, 2. So the advantage of Prolog to SML is the fact that you basically, in SML, you have inputs and the function returns an output. In Prolog, you are proving theorems. So you can actually ask queries like, what can you prove for append? And it will try to bound it with each one of the rules. And if this, like in the first rule, L is equal with L, it will actually succeed and return the empty list, but it doesn't. So it goes on the second branch. It basically bounds X to the list that contains the head H and the tail T. And this is the list L. And then this is the list H followed by T2. So now T2 is 2, 3, 4. And it will query recursively what can be appended as a tail T to L, which is 3, 4, such that the result is 2, 3, 4. and this will basically run recursively until it finds the result and returns the result. So the advantage of Prolog is really that you can actually ask all kinds of queries where some arguments are bound to lists or constants and some are variables. So for instance, the second query that you see here, it will return that all the possible lists x and y, such that the concatenation of the two lists is the list 1, 2, 3, 4. Or you can actually bind some arguments and some not. So let's actually test it. So again, we are going to write it first in Prolog. And we already did. So now we reload the program and we can ask these queries. What is the result of appending 1, 2, 3 with 4, 5, 6? And that will tell us 1, 2, 3, 4, 5, 6 and nothing else. What is the result of append of x and y such that the result is 1, 2, 3, 4? And it will tell me that x could be empty and y could be 1, 2, 3, 4. Concatenating the two is 1, 2, 3, 4. But another possible result is that x could be the list that contains 1 and y the list that contains 3, 4. Another possible result is that x is the list 1, 2 and y is the list 3, 4, and so on. It will give me all the possible lists whose concatenation is 1, 2, 3, 4. Okay? And I can actually give one bound, like for instance this is the list 1, 2, and one free, in which case it will tell me what's the one that is free. Similarly, what x can I bind with the list that contains 3, 4, such that the result is 1, 2, 3, 4, and tells me that x is 1, 2. So the advantage of Prolog is really that it uses theorem proving. So how does it work? A predicate is not a function. We are not applying arguments to get a result. We are proving that the theorem holds. Therefore, we can leave any variable unbound. So we can leave the first variable unbound, or you can leave the second variable unbound, or you can leave the first two variables unbound or free, and then it will give you all the possible results for that variable. So how does it work? Let's see it on an example. For instance, we call append of 1, 2 and 3, 4 with x, with the third argument x. So we said that we are matching the goal with the head of the rules. That was in the procedural semantics. So basically, the first rule does not match because empty list does not match the list that contains 1, 2. So the second rule matches with x bound to 1, is the head of the list 1, 2. L is the tail, so L is the list that is 2. And M is 3, 4. And the answer that we are looking for is the list that starts with 1, basically x, and has the tail n. And now we are asking the query in the body. So the new goal is, what can I append to, what is the result of appending the list L, but in our case L was the list 2, with the list M, which is 3, 4, such that the result is n. So again, the first rule does not match because the empty list does not match the list that contains 2. So it basically, x will be 2, and it basically matches the second rule, x is 2. The tail of the list that contains one element is empty, so this is a new variable L. Then M is bound to 3, 4, and x, the result n, will be a list that starts with x, which is in this case 2, and has a tail that is n prime. And now I am asking a new query. What is the result of appending the empty list, which was L in the previous case, with 3, 4, and the result is n prime, which matches the first rule. Basically, it matches the fact that empty list matches empty list. L must be equal with 3, 4, and n prime should be equal with L. So now on the way back, it computes all the answers. Basically, n was 2 followed by n prime, which was equal with L, which was 3, 4. So this was n is the list 2, 3, 4, and A is the list 1 followed by the tail 2, 3, 4. So A will be 1, 2, 3, 4. And this is how Prolog works. Any questions? I'm watching the chat on a different computer. Any questions? Okay, no questions. So let's see if we want to implement a length predicate. So to find the length of a list, we wrote it in SML as the length of the empty list is 0, and the length of a list that contains at least a head and the tail access is n plus 1 if the tail has a length of n. And now if we were asking the length of the empty list, it will respond 0. If we are asking the length of the list that contains 4 elements, is it 4, it will respond false. So why is that? The reason is that by default Prolog does not interpret addition. Basically, for Prolog, plus is just a symbol, is just a predicate symbol. So it has no meaning beside the predicate itself. In fact, if you write x is equal with 1 plus 2, it will return that x is the functor plus applied to the arguments 1 and 2. So matching does not do mathematical operations. So in Prolog, if you say x matches 1 plus 2, it will just succeed with x is 1 plus 2. It does not evaluate addition. It's just used for constructing data structures. But Prolog has a special built-in predicate called is. Is evaluates the right-hand side expression, and then it matches it with the left-hand side. So the general form for is R is an expression, where E is an arithmetical expression. That expression will be evaluated, and then R is matched with the value of that expression. So it expects that all the variables on the right-hand side are bound variables. If x would be a free variable, then it will give an error because it doesn't have a value yet. So if we write x is 1 plus 2, then it actually evaluates 1 plus 2, which basically means that it is easy to write a length predicate. We can say that the length of the empty list is 0. The length of a list that contains the head and the tail access is m. If we can compute the length of the tail access as n, and m is n plus 1. Basically, now we know the value of n, and m will be matched with the result of the addition of n plus 1. So now if we are asking, is it true that the list has the length 4, it will respond yes, because it will basically compute it and give us the value. Again, the advantage of Prolog is the fact that we can actually construct lists. So we can actually ask what is a list whose length is 4. It will give us a list with 4 empty or basically variable arguments. It will actually construct the list that has 4 elements. Okay. So again, let's return to our example. So we wrote length of the empty list is 0. We would have done exactly the same in SML. In SML, we would have written the function length applied to the empty list is equal with 0, and then we would have written or the length of a list that starts with the head x and the tail t is equal with 1 plus the length of t. We do the same in Prolog. The length of a list that starts with the head h and the tail t is m if the length of the tail t is some n, and now we know the value of n, so we can assign m is n plus 1. So This is the program that we just wrote. If we compile it in Prolog, we can now see that one warning that it tells us is that age is a singleton variable. So we can actually see now that it's useful to use anonymous variables. Basically, if we don't use the value of the head, we don't care about the head, we should use an anonymous variable. And now we can ask, what is the length of the list that contains 1, 2, 3, 4? And it will respond that is 4. And if we want to construct lists, we can ask, what is a list whose length is 4? It will respond, here is a list whose length is 4. Basically, it will give me a list with 4 variables, can match anything. Okay. Any questions? Okay, so Prolog also has what is called a conditional operator. It's an if-then-else construct. It basically says if A is true, then execute B, else execute C. In Prolog, this means try first A, then with the arrow, with dash greater than. If you can prove it, then go on to prove B, else ignoring B, execute and ignore C. If A fails, however, go on to prove C. So for instance, if I want to write maximum between x and y, compute it in the value of z, I basically check if x is less than equal with y, and the sign is actually equal less, because less than equal is used for DCG grammars, which is a different issue in Prolog. If x is less than equal with y, then z is assigned y, else z is assigned x. So let's actually test this predicate. So maximum between x and y is z if, and here the predicate was if x was less than y, then the maximum is x, z is unified with y, else z is unified with x. And let's load it again, and what's the maximum between 1 and 2? And it succeeds, that is 2. What's the maximum between 3 and 2? Is 3. So this notation basically uses arrow for the then part and semicolon for the else part. Many people actually prefer to basically use indentation and then basically have the two cases. Other people prefer the notation where the else is in the same line with the original condition. I would recommend to use just conditional statements with parentheses. This is an easier to see grouping. You can also put parentheses if you have conjunctions in each of the cases. This again used for grouping. And let's execute it one more time. It's the same thing. Okay. Okay. You can use these parentheses, these conditional expressions also for computing factorial. So if you compute n factorial, you can write it recursively as if n is less than equal with 0, then the factorial is equal with 1, else factorial is n multiplied with factorial of n minus 1. So factorial of n is f. If n is greater than 0, then n1 is n minus 1. We compute factorial of n1 into f1, and f is n multiplied with f1. And then otherwise, if n was not greater than 0, then f is equal with 1. Other imperative features of Prolog is backtracking. So for instance, earlier today we saw that we can actually print all the solutions of a query by running that query writing the result and failing explicitly, which is a predicate that always fails. It basically causes backtracking. If we don't want to backtrack, that means that you don't want to go back and execute a query, there is a special operator, cut, which prevents other rules from matching. We will see it later in an example. So the arithmetic operators allowed by Prolog are plus, minus, multiplication, division. They actually do automatic detection of integer floating point, and they will actually divide an integer or floating point. The integer operators for obtaining the quotient and the remainder are double, forward slash, and mod for modulo, same in SML if you remember. The comparison operators are less than, greater than, less than, equal, greater than, equal. There are also two operators which actually evaluate both expressions, and basically evaluate both expressions and then check if they are equal. Similarly for the operator checking that they are not equal, the equal, forward slash, backward slash, equal. So how do we program with lists? Basically the same way that we did in SML. We can do sorting, and this is an example of quicksort. Quicksorting empty list is empty list. Quicksorting a list that contains a head x0 and a tail xs is a list ys. If we can partition using the pivot x0, the list xs, into less than elements than x0 and greater elements than x0, we can quicksort the less than elements into tail ys and the greater than elements into a tail ys2, and then appending ys1, the less elements sorted, with the list that contains the head x0 and the tail ys2, which are the greater elements sorted, is the list ys. And that basically gives us the sorted elements. So now the other predicate that we have to define is partition. So given a pivot, we can partition the empty list into empty list less elements and empty list greater elements. Partitioning with the pivot a list that contains the head x and the tail xs is a list that contains the head x and the tail ys. So basically, if x is less than the pivot, we put it in the less elements, and we partition the rest of the list xs into less elements ys and greater elements zs. Partitioning in the case that x is greater than the pivot, if x is the first element of the list, if x is greater than the pivot, we put x in the greater elements, and we call recursively partition of the pivot the tail xs and the less elements ys and the greater elements zs. So this basically does quicksort, and we can implement also merge sort if you remember from SML, select sort, and so on. Now we can introduce cut. So one thing that we observed in the previous case is that the Prolog system will try both rules for partition. But what if we don't want to do this check again in the second rule? We want to say that in case that x is less than the pivot, execute this rule, otherwise execute the second rule. We can do it with a cut predicate. The cut predicate basically says that if the first rule succeeded, then only try this rule, never go back. So if this didn't succeed, then we don't reach the cut and we actually execute the second rule. So what this does, it basically cuts part, it prunes the tree that we saw in the case of the bear earlier. So if we know that one answer succeeded, like in the case of this SLD tree, select resolution tree, we basically, if we succeeded on one path, then do not try any more paths. That's what the cut predicate does. It basically says do not prune you don't execute the second partition. Okay? So this cut predicate, we will learn it later. It basically says only succeed once. Do not try other rules. Okay? So before we continue, let's see an example of cut. So let's assume that we have some predicate P, and P was true for 1, is also true for 2, 3, and so on. And now in our Prolog program, we reload the program and we ask, what is P true for? And it will tell us it's true for 1, 2, and 3. But what if we say what is P for true, and then stop, cut the rest of the execution? It will tell us that it's true for 1 and nothing else. So this cut basically says do not backtrack anymore. That's what it means. Do not backtrack. It's an imperative feature that tells the Prolog system that after you found a solution, do not go back, because we are not interested in other solutions. We are only interested in the first solution that we obtained during execution. Okay? Okay. So, any questions up to now? Okay. Now let's write a different predicate. Let's define the predicate delete. Given an element, we want to delete that element from the list and obtain the rest of the list. So this delete should succeed and return the rest of the list. But of course, because we are in Prolog, we can give it with other queries. Like for instance, what element could I have deleted from the list 1, 2, 3 such that we get the list 1, 3? Or from what list I could have deleted 2 such that the result is 1, 3. And it will actually return all the possible lists, basically, in which 2 can occur before 1, 3, between 1, 3, and after 1, 3. 2, 1, 3, 1, 2, 3, and 1, 3, 2. So it basically gives me all the possible lists from which I could have deleted 2 to obtain the list 1, 3. So as you can see, basically, if we have the element repeated, it will actually return all the possible answers. It will tell me that if I delete the first 2, I get the tail 1, 2. If I delete the second 2, I get 2, 1. So the algorithm is that you can delete the head of the list, in which case the tail of the list results as the rest of the list. Or you can delete from the, if you want to delete X from the list H that starts with the head H and the tail XS, you can delete X from the tail of the list, in which case you get the result, the list that starts with the head H and the tail ZS, where ZS is the result of taking X from the tail YS. And that is exactly this program. Basically, one rule could be an explicit rule that fails. It says that X cannot be deleted. If you try to delete X from the empty list, you cannot do it. You should fail. And this is not needed because by default, Prolog always fails when it cannot do an operation. So the first rule is actually not even needed. We can omit it. But the second and third rules are basically saying that we can delete X from the list that starts with X, and we obtain the rest of the list, the tail of the list. Or we can delete X from a list that starts with the head Y and the tail YS. If we delete X from the tail YS, and we obtain a list ZS, and then deleting X from the original list is the list that starts with Y and the tail ZS. And that will actually delete, for instance, S from the list LIST and give us the list LIT. We deleted the S. But we can also give other queries. What could I have deleted from this list and got what tail? In which it will delete by, it will tell me that X could be L and then Z is IST. Or X could be I and Z is LST, and so on. Okay, so let's actually write this program. This program is in fact very useful for many predicates that use backtracking in Prolog. So let me just write these two rules. So we can see that there are two rules. One deletes X from the head and returns the tail, and one deletes X from the tail and returns the list that contains the head and the resulting tail. So in Prolog we recompile test and we can ask delete 1 from the list 1, 2, 3 and give me the rest. And it gives me 2, 3 and nothing else. Delete 2 from that list and it gives you 1, 3. Delete 3 from that list and it gives me 1, 2. Similarly, I can ask what could I have deleted from the list 1, 2, 3 such that I get the result 1, 3. And in this case it tells me 2. So I can bound the second and third arguments and leave unbound the second argument. Moreover, actually I can ask what I could have deleted from the list 1, 2, 3 and what is left. And it gives me that if I delete 1, I get 2, 3 in the rest. If I delete 2, I get 1, 3. If I delete 3, I get 1, 2. And now, from which list I could have deleted 1 to obtain the list 2, 3? And it tells me from 1, 2, 3, or from 2, 1, 3, or from 2, 3, 1. And nothing else, because deleting 1, it will always result in the list 2, 3. In fact, the good thing about Prolog is that you can actually bind and unbind any elements of Prolog. So in fact, now I just asked, give me from what list I can delete what element and I get what tail. And it will tell me that if I delete the first element, then I get the tail as the rest of the list. But I can also get more of such answers. Basically, all the possible lists from which I can delete all the possible elements and what are the rest of the lists returned. Okay. So Prolog is extremely powerful. It's probably in this respect one of the simplest languages with the highest power. So now let's think about more complicated examples like permutations. We want to define permute to find the permutation of a given list. Like for instance, if I ask give me the permutations 1, 2, 3 of the list 1, 2, 3, it should return upon backtracking the list 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Now, how can we write it? We can think of recursion. Basically, take the element the head out, which is 1, compute recursively all the permutations of 2, 3, which are 2, 3 and 3, 2. Next, if you insert with our delete predicate that we defined before 1 into all the possible positions in these two permutations, we get in fact all the permutations of 1, 2, 3. So we can write permutations simply as follows. Permutation of the empty list is empty list. Permutation of a list that starts with the head X and the tail XS is a list YS. If permuting the list XS is a list ZS, permuting the tail is a new list that is a permutation of the tail. And deleting X from YS gives me ZS. So basically this will call this delete predicate that we had as the last call that we had, basically delete with 1 bound and the tail, which is the permutation, which will give me all the possible basically insertions of that one element in the permutation. Okay, so basically if we call recursively permute of 1, 2, 3, it will give me all, it will take 1 out and then we will compute the first permutation of 2, 3, which is 2, 3, and then insert 1 before 2, 3, between 2, 3, and after 2, 3. and then it will give the other permutation through backtracking of 2 3, which is 3 2, and then insert 1 before, between, and after, and that gives me all the permutations of 1 2 3. So the delete predicate in this case is used with the first and the third argument bound, and it will result in all the insertions of the first argument in the second argument in the list, that is the third argument. Okay? Which is much more simple that you would write it in any other programming language. Like for instance, I usually show how to write it in Java, and in Java the same program for permutations would take at least 50 lines of code, because this works for any type. So in fact it will basically do the same algorithm, but you have to construct array lists of objects in the most general case. Okay? Any questions? Okay, great. So we can continue with the issues of efficiency. Now, if we try to write the predicate to reverse a list, reversing a list basically will put the first element at the end, and then it reverses the tail of the list. So if we write it in a naive way, reversing the empty list is the empty list. Reversing a list that starts with the head x and the tail xs is a list ys. If reversing xs is a new list zs, and then appending zs to x is the list ys. Now, if we look at how long this predicate will take, we will see that recursively reversing a list of n elements is the time that takes to reverse a list of n-1 elements plus the time to add the last element at the end, which is in the size of n-1, because we are actually using append in this case. So t of n is the time of n-1 plus n-1. And if we keep unfolding up to the element of the list of empty list, is basically always it's n-1 plus n-2 plus all the elements up to 1, which is quadratic time. Is O of n squared, is n multiplied with n-1 divided by 2. But that's definitely not acceptable. We don't want to get quadratic time, square time for the reversing a list. So how can we do it? We can keep an accumulator. That means we stack all the elements seen so far in an accumulator, and as we take elements from the head of the list, we put them in the accumulator. We will get the elements in the accumulator in reverse order. So reverse of two lists will call reverse of the list and the empty list as accumulator, and the list that will be the output, which will call the reverse helper relation with a list. If that list contains one element, then we take the element and we call recursively the helper with the tail xs, the accumulator with x as the first element and the previous accumulator as the tail and the out variable, and we stop the moment that the list is empty, the first argument is empty. In that case, the accumulator is matched with the out result and we return the result. So for instance, reverse of 1 2 3 will call reverse helper of 1 2 3 empty and x, which will use the first rule, and will call reverse helper of 2 3 the tail of the original first argument, and 1 pipe the empty list, which is the list that contains 1 and x, which will call the helper relation of 3 and 2 1 and x, which will call the helper method of the empty list, the list 3 2 1 and x, which succeeds with x equal with 3 to 1. So this will make it to actually run in linear time. But in the most general case, we actually need to always have access to the last element of a list, which we can do, we will see later, with a difference variable. A difference list variable uses a variable at the end of the list, as the tail of the list, and it passes that variable as a separate parameter, which basically gives us an access point to the end of the list. Suppose that we represent binary trees, and we'll see in the sample exam that we'll discuss on Monday such an example. Basically, we can use nodes, predicates to represent internal nodes, meaning that we have the node and its children. We have leaf predicates for those nodes that do not have children, and we can represent a graph like the one that we have on the left hand side as a tree, as a set of facts. So for instance, this binary search tree is represented as 5 is a node that has the children 3 and 6, 3 is a node that has the children 1 and 4, 1 is a leaf, 4 is a leaf, and 6 is a leaf. We can write predicates for pre-order, post-order, and in-order, which basically return in a list the elements of that tree. So if the root is a leaf, then we return the leaf in a list. If the root is basically a node that has child 1 and child 2, then we can read in pre-order child 1, we can read in pre-order child 2, we can append L1 with L2, the pre-order of child 1 and child 2, into a list L, and then the result of pre-order of the root is root followed by L. So for instance, for the tree that we saw before, we can ask, can you give me in pre-order from the root? And it will give me the list of nodes 5, 3, 1, 4, 6. The program again takes O(n) squared time. The reason why is that it has to do this append. So how can we do appending of lists in shorter time? The answer is difference lists. So the lists in Prolog are single linked. We cannot access the last element. We basically can access in constant time the head of the list. In order to get to the last element, we have to scan the entire list. However, unlike functional programming languages like SML, we can have variables in data structures. So if we have a list in which we have a variable at the end of the list, then we can access the end of the list. We can actually assign a different value to that variable at the end of the list. So let me show you an example. For instance, I have the list L as the list that contains the elements 1, 2, 3, 4, 5 with the tail T. If I'm also given the tail T as an argument, later I can actually add more elements at the end of the list. I can say that T is 6, 7, 8 followed by a new variable tail 2. And now basically the list L will be 1, 2, 3, 4, 5, 6, 7, 8 with the new tail, which is T2. T2 has the variable 351, which we can see here. So difference lists take advantage of the fact that you can have variables at the end of lists, and these variables can be basically later assigned different values. So if we have a list that ends with a variable, like X is a list that contains 1, 2, 3 and ends with the variable Y, we can now follow up with new values for Y. We can say that Y is the list that starts with 4 and has the tail Z, in which case it also makes X the list that contains 1, 2, 3, 4 with the tail Z. We can now think of Z as a pointer to the end of the list X. So we can continue adding elements in constant time. Basically we can add now, assign now or match Z with the list that contains 5 and W. So now the list X will contain 1, 2, 3, 4, 5 with the tail W, with the variable at the end W. Which actually gives us a way to actually access and add elements at the end of a list. But which means that any list, difference list, is represented by two variables. One that refers to the entire list, and another one which is the uninstantiated tail. So for instance, X could be this list with the tail Z. Most Prolog programmers use a notation list minus sign tail, which denotes the list with the variable tail. So instead of passing two arguments to a predicate like a list and end variable, they pass one argument, which is a structure, is the minus symbol, infix symbol, not the arithmetical operator, with the first argument, the list, and the second one, the variable at the end of the list. So for instance, append can be done in constant time in this case. So if I'm given a list with the end variable t and another list y with the end variable t2, then the result will be a list with the end variable t3. If I bind the tail t with the variable y, so basically in this case it will continue x with the elements of y, the tail t3 with the tail t2, and l to the result variable with the variable x. In that case, if I call append of 1, 2, 3 with the tail t, 4, 5, 6 with the tail t2, and it will respond that L, it has the elements 1, 2, 3, 4, 5, 6 with the tail t3. The simplified version, because all that we do in this rule is matching variables, so we basically say that t is the same with y, t2 is the same with t3, and L is the same with x. We can write that same append with appending x with the tail t, with t with the tail t2 is x with the tail t2. A more simplified notation using minus, the infix operator minus instead of comma between the list and its tail, is appending a list x with the tail t with a list t with the tail t2 is a list x with the tail t2. So we can write it in a single fact, and it will actually do the concatenation of the two lists in constant time. So then we can actually write all of our predicates that were previously done for normal lists in linear time or quadratic time in almost constant time. Because as we can see, if we want to add an element at the end of the list, we can basically just add it by specifying that t, the variable tail of the list, is a new list that contains x as the first element at the tail t2, and t2 will be the tail of the new list. So we basically, the list L2 is L. So we can simplify that into the notation where L is replaced by L2 is replaced by L, and even more, we can replace t with the list that contains x and t2, which gives us in a single predicate rule, basically the appending or the adding an element at the end of the list. So now we can actually also write an alternative version of adding an element at the end of the list, which uses append. So we can append a list, the original list, with the list that contains x and the tail t2, and it will give us the list that contains all the previous elements with the new tail t2. Palindrome can be written in the same way. So one definition of palindrome, which is a simpler definition, is that you reverse the list and you check that the list is equal with its reverse. But another way is basically to check if the list is a palindrome with different lists. I will do the previous version. So let me actually copy this and just do palindrome with reverse. So one way to do palindrome is to check that the reverse of the list is itself. And the other way is with difference lists. And in fact, let's take this slide and put it after we talked about reverse. So this was the reverse, and now we can do palindrome with reverse. Okay, good. Okay, so how do we represent graphs in Prolog? We can represent edges as facts, or the entire graph as a single data, as a single structure, which has the nodes and edges and lists. And we can also represent them with adjacency lists, basically, then for a list of nodes with their destinations. Basically, we have edges from A to B, from B to C, and to F, and from D we have no outer edges. So for instance, if we want to find paths from one node to another in a graph, we can write a path predicate where we can pass the graph in the previous notation with the list of nodes and the list of edges. We can give the beginning edge and the end edge, and the result will be a list of the path, the nodes that takes us from A to B. And we can find all such paths via backtracking. So we will solve it with the graph as a data object, like the graph is the set of nodes A, B, C, D, F, G, and the edges are from A to B, from B to C, and B to F. First, we have to decide if this is a directed graph in which we only consider direct edges. If in the edges we have the edge from X to Y, or if we consider the edge from X to Y and the edge of from Y to X as basically reverse edges. This would be in an undirected graph. But in either way, we can write path as a recursive reachability relation. Basically, we can find the path from A to B if we can find the path from A to the path, the partial path that is as the first element B. The path helper succeeds in the moment that we reached in the path that we obtained, the first element is A. If we did that, the path is actually saved and returned. Otherwise, there is a path from A to Y if A is adjacent to Y. Actually, this should be X. No, if there is a node, sorry, it's correct. If there is a node X such that X is adjacent to Y, and X is not a member of the previously seen path, or and we find the path from A to X. So basically, this looks from the end to the beginning. It basically looks at the end and finds nodes that go to the last node, and then we find paths from the beginning node to those nodes. We can also find cycles by basically finding all the possible nodes. If we find a path from A to B, and we know if there is an edge from A to B, and we can find a path from B to A in reverse order. This is only for directed graphs. And the complete program is given in the lecture notes. Basically, it's a directed path program. We have adjacent for directed paths, and then we have the path predicate, and we pass the graph as a parameter, as a data structure. So as I said at the beginning of the class, findAll finds all the possible answers to a query and collects all the results in a list. There are variants of findAll, setoff, which also basically finds unique answers to the goal, bagoff, which has the same semantics with setoff, with the exception that the third argument is an unsorted list, and tfind, which is tabled for AccessBeProlog. And there are examples in the lecture notes. Finally, negation. So negation is basically negation as failure, which basically finds all the possible answers in which the predicate that we pass as the predicate inside the negation is not provable true. We can read and write to files either in two different formats. The cut symbol we will discuss next class at the beginning, and that is basically the last important fact. The rest are just about predicates in Prolog. Okay, that's all that it will be in the final exam, and next class we are going to do several examples of Prolog, including all the examples that we did in SML. That's all for today. Thank you very much. I will save the recording and put it on YouTube. Bye. Yes, I will post it.